When gazing at the sky on a clear, starry night, it is pretty clear that space is vast. But just how vast is it? The stars may seem brighter and closer than other stars on some nights, but traveling to the nearest star beyond our sun would take 70,000 years. To give another perspective, our galaxy of stars, called the Milky Way, is so huge that even at the speed of light, it would take 100,000 years to travel across it. This is just one galaxy. There are billions like it in the universe, but we can only see the ones whose emitted light has reached Earth. These visible galaxies make up our observable universe. So what is the observable universe? The term is just that, what we can see in our universe when looking out in any given direction. These observations are relative, meaning that the Earth is at the center of its observable universe. Observations made from another planet or galaxy would make them at the center of their observable universe. The size of the observable universe is determined by the speed of light and the rate of expansion. Light travels at a constant 186,000 miles per second. This is incredibly fast. We can never use light to see past the farthest distance it has had time to travel. Scientists have estimated that the universe is 13.8 billion years old. This estimate is based on how long it takes for the light emitted at the very beginning of the universe to reach the Earth. Abiding by the theory of relativity, we'll never be able to see beyond that boundary. This essentially means the observable universe is the only universe we'll ever interact with under these known principles. So what exactly do we see within this limited space? Before talking about observation on a cosmic level, let's start smaller. We see objects and people on Earth every day. However, the image we see compared to what actually exists is delayed. Every photon our eyes see, an image our minds perceive, are actually as old as the time it took for that light to reach our eyes. This is not a very large discrepancy, and our brain can't even account for it. When this principle is applied to the entire universe, this discrepancy grows exponentially. Let's start with the sun. The sun is 109 times the size of Earth and is 93 million miles away, which is why it looks so small in the sky. The light from the sun does not reach us the instant it is emitted. It actually takes a little over 8 minutes. So the light from the sun and the image we get from the light is actually 8 minutes old. Therefore, when we say the photon is 13.7 billion years old, this means that the light emitted from this time has taken that long to reach the Earth. The light that reaches us from faraway galaxies took millions of years, which means what we see today shows how these galaxies looked millions of years ago. So we can't see the universe as it currently looks today using light, but rather how it looked millions or even billions of years ago when the light that reaches us was first emitted. Interestingly enough, some light may never have enough time to reach us because the universe is constantly expanding. To explain expansion, we have to first discern years and light years. Remember, photon can be 13.7 billion years old. However, it may have traveled 45 billion light years, a distance, from its origin to the Earth. Therefore, a light year measures how far light travels in a vacuum in 1 year, or 6 trillion miles. Now let's go all the way back to the beginning. Right now, the best theory scientists have for the start of the universe is the Big Bang. The name Big Bang is a bit misleading. It is not an explosion, as the name suggests. Instead, it was a spontaneous and rapid expansion of every point in the universe. Think of it like a tiny balloon in which the air inside is the universe. It starts off as a small, compact singularity and then expands as you blow into it. This didn't stop as soon as galaxies and other masses started forming. Expansion is still happening today. The very fabric of the universe, called space-time, is always expanding, meaning that every point in it, every star, planet, and galaxy are steadily moving away from each other. Imagine a photon starts off from point A, thinking it has to travel 4 million years to point B. By the time it travels 4 million years, point B has expanded to 10 million light years away. Although the photon sees that it has traveled even more than the original 4 million years, it still isn't even halfway to point B. Because of expansion, the light will continue to get closer to point B, but at a constantly decreasing rate since expansion is constantly occurring. So you might be thinking that if the photon is still moving towards us, just at a slower rate, then we can just wait for the light to reach us eventually, and we'll have a larger observable universe, right? Not exactly. Expansion has another effect at a smaller level called redshifting. A photon of light is a particle, but also behaves like a wave. As this wavelength is emitted over a farther and farther distance between point A and point B, its frequency also gets lower. This means not only that the photon has farther to travel, but also that it has shifted on the light spectrum towards the lower, redder frequencies, hence the name redshifting. But it doesn't stop at red. The farther away sources of light are, the more redshifting occurs. After a certain point in time, the waves shift out of the visible light spectrum. This is why the wavelengths may be in the form of radio waves or other low frequencies like microwaves. It is because of redshifting that we will never be able to see the entire universe by observing light regardless of time, because the photons will take such a long time to cross the ever-expanding distance that they will not even be in the form of visible light when they reach us.